last week we defined the derivative. Now remember, the definition of the derivative is actually a limit. And we've seen from our study of limits that a limit doesn't necessarily always exist. So we're going to apply that to derivatives. And we'll start with this definition. We say a function is differentiable at a point if f prime exists at a point. Now this definition is written to actually define differentiable in two ways. So the one way, we say f is differentiable at a point A if f prime exists at a point A. And the other way we read this is we say f is differentiable if f prime exists for all x in the domain of f of x. So it can be read one way with parentheses, it can be read another way if you ignore the parentheses. And there's a theorem in mathematics that if a function is differentiable, meaning if its derivative exists on its entire domain, then the original function is continuous. However, the converse of that statement is not necessarily true, and we'll see an example of that. The converse being, if f is continuous, then f is differentiable. That statement is not necessarily true. And we'll look at an example that we have seen. So let's call this example. Example, f of x equals the absolute value of x, and here we'll write out the actual definition of the absolute value of x. Remember, the absolute value of x is x if x is greater than or equal to 0, and it equals negative x if x is less than 0. And we're going to show that this function is not differentiable. Now, to show it's not differentiable, we need one point in its domain where the derivative does not exist. In this case, we will show that the derivative does not exist at 0. So let's do that. Well, let's write that down first. F of x is the absolute value of x is not differentiable at x equals 0, at a equals 0. Let's say at a equals 0, because I used a in the definition of differentiable. F of x is not differentiable at a equals 0. Well, to do this, we need to try to find the derivative at 0 using the definition. So let's do that. Now, when we first defined the definition, we had the one with x plus h, f of x plus h minus f of x all over h, the limit as h goes to 0. But to define the slope of a tangent line, we also used a second definition. So for this one, we're going to use that second definition. You could use the first definition, I think, or you could use the one with h, or you could use this one. I think this one is slightly easier, so let's do that. F prime at 0 equals the limit as x approaches 0 of f of x minus f of 0 all over x minus 0. I miswrote that. F of x minus f of 0 all over x minus... I said it correctly, I just miswrote it. And now, well, what is this? Well, f of x is the absolute value of x. Haven't taken a limit yet. So we have absolute value of x minus f of 0. Well, the absolute value of 0 is 0. I guess I'll write that out. Over x minus 0. And what does this simplify to? Well, the absolute value of 0 is 0 from the first part of that. So this is the limit as x approaches 0 of absolute value of x over x. So now what we need to show is that that limit does not exist. If we show that that limit does not exist, then we will be able to conclude that the absolute value function is not differentiable at 0. And then we will be able to conclude the absolute value function is not differentiable. And then we'll be able to conclude that there is a continuous function which is not differentiable. And we know this is continuous because we've seen its graph before. I should probably leave that definition up here. So I'm going to do that. If x is greater than or equal to 0, if x is less than 0. We want to show that that limit does not exist. Well, you try substituting. You get 0 over 0. When you get 0 over 0, we're going to do some algebra. But in this case, we're actually going to look at both sides of 0 because the absolute value function is defined differently on both sides of 0. So maybe I'll say which does not exist from the work we're about to do, or by the work we're about to do. So which does not exist since the limit as x approaches 0 from the right of absolute value of x minus x. We're going to show that the limit on the right does not equal the limit on the left. Well, on the right of 0, how is this function defined? Well, the function is defined as just x on the right of 0. So we get x over x. We still haven't taken a limit, but now this fraction reduces to 1. We still haven't taken a limit, but that fraction does reduce to 1, and the limit as x approaches 0 of 1 is just 1. And now we do this on the other side of 0. On the left of 0, how is this function defined? Or how is the absolute value defined? Well, on the left of 0, we get negative x. I should have written that so it was directly under. I'm going to leave a gap there so it's still directly under. So now we have negative x, but this right here is a fraction, and that fraction reduces to negative 1 because the x's cancel and you're left with a negative 1. As x approaches 0, negative 1 approaches negative 1. So right here we have the limit on the left does not equal the limit on the right. So that initial limit doesn't exist, so the absolute value function is not differentiable at x equals 0, or a equals 0. I guess the actual letter we chose didn't matter. So let's consolidate that as a remark. Remark. Oh, maybe I should draw a graph first. Okay. F of x equals absolute value x is a continuous function which is not differentiable. Why is it a continuous function? Well, what does the absolute value of x look like? Looks like that, and it looks like that. So you can draw that without lifting your writing utensil. So is continuous. So this function provides a counterexample to the previous theorem's converse. Now, we can actually see what happens at 0 in this graph. Now, remember what the derivative gives. The derivative gives you the slope of tangent lines at a given point. Well, what was that computation we were doing? We were looking at the slopes of tangent lines on both sides of 0. Well, the slope of the tangent line, say here, is positive 1. The slope of the tangent line here is positive 1 also. I mean, it's positive 1. Let's just pay attention to the fact that it's positive. Right here, slope of the tangent line is also positive 1. And we saw that in our computation. The limit on the right of 0 was 1. Over here, the slope is negative 1 in particular. Here, the slope is negative 1. Here, the slope is negative 1. And you can see that this absolute value function could help us find a general type of function which is continuous but not differentiable at 0. So let's write that down. How do I want to write that down? This is how I want to write that down. The following, I'm going to say are. I'm going to start with is, but I'm going to be drawing a couple different graphs. So I'll say the following are graphs of functions which are continuous but not differentiable. Well, the following are graphs. Here's one of them. Where do I want to put this? Let's do it like this. Something like this. We'll call that point A. Right here, the function is not differentiable at that point A because the slope on this side is positive, the slope on this side is negative. And we're going to call this a corner. So I'll say the following are graphs. So 1 is a corner. If the function has a corner like that, the derivative will not exist. The second one will look something like this. We'll call that point A. So right here, what do the tangent lines look like? Well, the tangent line here is a positive number. Tangent line here, a positive number. But notice, it is getting larger. Tangent line here, a positive number. So on the right of A, these tangent lines, the slopes of these tangent lines start as positive numbers, and then as you get closer to A, they become larger positive numbers because the slopes are going, they're starting, well, let's just use this. They're starting like this, but then as you get closer to A, the tangent lines are getting more like that. So they start like this, a positive number. As you get closer to A, they become more positive. So the slopes on that side go to a positive infinity. On this side, they start as negative, and then they keep becoming more negative. So right here, we have a slope like this, a negative number. Right here, you have a slope like this. It's more negative. Right here, the slope was like that, or the tangent line was like that. As you get closer, it becomes more sloped, becomes more negative, the slope. So you can see on both sides of A, the slopes of the tangent line do not approach the same number. Because on the one side they approach a positive, on the other side they approach a negative. And we're going to call this a cusp. And in math, the treatment of infinity is, well, infinity tends to result in additional cases that just finite numbers do not result in. And this is one of them. This third example of a continuous function which is not differentiable would look like this. Right here, this is an example of a function which would have a vertical tangent. So at A, the tangent line is vertical. On this side, the tangent lines approach a positive infinity. On this side, they also approach a positive infinity. We're going to, for the purposes of this, we're going to assume that that means the function is not differentiable. And a vertical tangent will give us a third example of a continuous function which is not differentiable. If you want an example of, well, an example of this would be, what, the square root function and then a square root of negative x at 0. Here you could use the cube root of x at 0. So these three types of examples are important to know, that a corner and a cusp in particular, and a vertical tangent, are continuous functions which are not differentiable. And definitely for the absolute value, it's good to be able to go through that argument with the definition.